Hello. We're going to continue our discussion about convergence by looking at a few tests where we can test for the convergence whether our terms are positive or negative. And the first test we'll use is known as the alternating series test. And the alternating series test has three conditions. First, that the terms of our series must in fact alternate. You'll spot this often by seeing a power of -1 in your nth term expression. Second condition is that the terms must decrease in absolute value. So we say the terms must get smaller in absolute value, and symbolically we would represent that by the expression the absolute value of the n plus first term must in fact be smaller than the absolute value of the nth term. Finally, very important, the limit of the terms must be 0. So symbolically we would write the limit as n goes to infinity of the nth term must in fact be 0. And if a series has all three of these conditions, then the limit of our sequence of partial sums will exist. A number line is a good way to visualize what's going on and why this test works. If we have our number line and we start at 0, and let's let our first term be positive, might as well. And when we put in our first term, we move out here somewhere on our number line, and we get to our first partial sum. When we add in our second term, which we know to have a negative sign, we're going to go back towards 0, but we're not going to go as far back as we moved with our first term because we know our terms are getting smaller in absolute value. So we'll move back maybe to here. There's A2, giving us S2, our second partial sum. Moving back the other way, we won't go back as far as we moved with A2, so we'll get S3. Back again, not as far, we'll get S4. And you see, as we continue this process, we will be zooming in on some sort of limit that we get closer and closer to as we add these smaller and absolute value terms to our partial sum. We say, let's look at the classic example of the alternating series test, and that is to confirm that this alternating harmonic series, 1 minus a half plus a third minus a fourth, and so on, does in fact converge. And it converges because of this alternating series test. Terms are getting smaller in absolute value, alternate in sign, and the term values approach 0. Please notice that this series will only converge if we add the terms in order so that we are creating this sequence of partial sums that has a limit. In fact, we call this property conditional convergence, the condition being that we add the terms in the correct order. You can explore on your own to find that if you add the terms of the alternating harmonic series out of order, you could actually create any sum you like. Also, if we took the absolute value of the terms of this series, we get the harmonic series, which does diverge. It's a property of series that if you did take the absolute value of the terms and you got a convergent series, then your original series would converge. So we put that property into play. That's known as absolute convergence, when the absolute value of the terms gives a series that does converge. The next test we're going to look at is known as the ratio test, and we will use the ratio test for absolute convergence, so we don't have to worry about the signs alternating. Ratio test for absolute convergence. The ratio test requires us to look at the ratio between consecutive terms, similar to the ratio we looked at with the geometric series, only this time we will not get a common ratio, but we will look at the limit of that ratio. And if that limit, as n goes to infinity, is less than 1, then our series converges. If that limit is greater than 1, then definitely our series diverges. Unlike the geometric series, it is possible for that limit to equal 1 and tell us more information. But this test will not do it. We'll have to use one of our other tests to determine what happens when that limit equals 1. So we will say here that our test is inconclusive, and we must keep checking what happens at those endpoint values. Let's look at a few examples. We're going to find that when we apply the ratio test to power series, we get a lot more information than simply knowing whether or not the series converges. So let's look at a few examples using power series. First power series let's look at is 1 plus x squared over 2 factorial and so on. We are going to apply the ratio test. So we look at the limit as n goes to infinity of the ratio of our n plus first term, which would be x to the n plus 1 over n plus 1 factorial, and then divided by the nth term. Usually we get these messy fractions, so I simply immediately multiply by the reciprocal of that nth term, which would be n factorial over x to the n, and we need that ratio to be less than 1 in order to guarantee convergence. Simplifying the x terms, x to the n plus 1 over x to the n simplifies to just x. N factorial over n plus 1 factorial simplifies to n plus 1. And we need to look at that limit as n goes to infinity. And no matter what x value we choose, n plus 1 is going off to infinity. So this fraction has a limit of 0. And since 0 is less than 1 always, we can say that our series converges for all values of x. Let's look at another example where we don't have all x's giving us convergence. If we have the series x minus x cubed over 3 plus x to the 5th over 5 and so on, you might look at this and say, well, why can't we apply the alternating series test? Looks like the terms alternate in sign. And in fact, for any values of x, they would alternate in sign. But we have that second condition and that third condition that the terms go off to 0. And in fact, depending on the values of x here, these terms don't go off to 0, and they don't necessarily get smaller in value. So we're going to use the ratio test yet again. Limit n goes to infinity, the absolute value of the n plus first term, so we replace all the n's in our expression with n plus 1. Negative 1 to the n plus 1, x to the 2n plus 1 over 2n plus 1 plus 1. And again, I will multiply by the reciprocal of the nth term, 2n plus 1 over negative 1 to the nth, x to the 2n plus 1. And we need that absolute value to be less than 1. Because we're dealing with the absolute value, absolute convergence, the negative ones are not important. We look at the x terms, x to the 2n plus 1 or x to the 2n plus 3 over x to the 2n plus 1 simplifies to x squared. And the limit of 2n plus 1 over 2n plus 3 is simply 1. So notice this time there's no more n involved in our limit, and so we just need the absolute value of x squared to be less than 1. In order for that to happen, we would need the absolute value of x to be less than 1. So now that we have this condition, we can see what we call for this power series the radius of convergence. In order for this series to converge, we need to be within 1 unit of our center at 0. It also gets us a head start on the interval of convergence, and that interval starts out at negative 1 less than x less than 1. And I say start out because remember we have to check what happens when our limit equals 1. So our limit of our ratio would equal 1 when x equals either 1 or negative 1, and we must check to see whether or not we have convergence at those endpoints. And we do that separately. At x equaling 1, what series do we produce? Plugging 1 into our expression, we get 1 minus a third plus a fifth minus a seventh and so on. And now we can use the alternating series test. Yes, the terms alternate in sign, they get smaller in absolute value and approach 0. So we do in fact have convergence at the right endpoint. And at the left endpoint, negative 1, we get the opposite of the same series. And so again, we have convergence. So now we can state the interval of convergence for this series. So our series converges for all values of x between -1 and 1 inclusive. Have a little visual that kind of illustrates this. That series happened to be the Taylor series for the inverse tangent. We have here the center, and we have an interval from -1 to 1 dotted off. And as we increase the terms, here's a first degree Taylor polynomial. There's our x. And third degree Taylor polynomial, x minus x cubed over 3. And you see, as I increase the degree of the Taylor polynomial, the green curve, which is our polynomial, approximates the red curve over a larger and larger interval, but not without bound. Because no matter how high a degree polynomial I choose, my Taylor polynomial agrees with my function between -1 and 1, but not any further. I can go all the way up to a 25th degree polynomial. And you see that as soon as we hit 1 or -1, we have definite disagreement between the two curves. So you're going to go practice using the alternating series test and the ratio test to check for convergence.